Hello. In the previous lecture, we were discussing continuity and differentiability. Uh, in the last lecture, we established open set characterization of continuous functions, and we also introduced the concept of differentiability in complex analysis. In today's lecture, we are briefly going to cover the remaining part of differentiability, and then we'll start with Cauchy-Riemann conditions. So far, we were last discussing one important point that if f has a derivative at z naught, if f has a derivative at z naught, then it is continuous at z naught. And I made a point, that the modulus of z serves as an example, where it is continuous at 0, but not differentiable at 0. Okay, so mod z is one example. I tried to compare it with modulus of x. However, I cannot compare because modulus of z cannot be graphed like this. Okay, but one variable calculus I can graph on 2 dimensions. So basically, y is equal to modulus of x. You know from your standard 12 that this is discontinuous, that this is non-differentiable at x equal to 0. However, it is continuous everywhere. But the problem with this particular function, that is modulus of z, you'll find that it is nowhere differentiable. It is nowhere differentiable in C. So the only example, so basically the complex analog map of the modulus function uh, turns out to be nowhere differentiable. However, it is continuous in C, but it is nowhere differentiable in C. In modulus of x, that is the real counterpart of modulus of z, uh, this is non-differentiable only at a point. Otherwise, it is differentiable. You can see that slope here is 1, that is y is equal to x, and slope here is -1, that is y is equal to -1. Okay. Now let us consider how to think about this. So consider fz is equal to modulus of z, and let us take any point z naught which is non-zero. We've already established that it is non-differentiable at 0. We are taking any point which is non-zero. Let us say I have taken a point z naught which is non-zero. Just kidding. Okay. So now let us take a point z naught which is non-zero, and I'm trying to see whether it is differentiable or not differentiable at any such point. So in order to have know the differentiability, we need to see whether this limit exists or not. And by existence, I mean it should exist independent of path. Okay. So let us take this particular thing, that is f of z naught plus h minus f of z naught. And it will give me limit h tends to 0. What is f of z naught plus h? I can write z naught plus h modulus minus z naught modulus divided by h. So what I'll do, I'll again take limit h tends to 0 I can multiply with, so what I'll do, I'll try to multiply this by z naught plus h modulus plus modulus of z naught divided by h into modulus of z naught plus h plus modulus of z naught. Now again, if you think what it will be, so the first part here would be simply z naught plus h mod whole square minus z naught square mod z naught square divided by h into z naught plus h modulus plus modulus of z. You know that what is mod z square? If you remember, mod z square can be written as z into z bar. So I'm writing it here only. So this will be limit h tends to 0. This is z naught plus h into conjugate. So this would be z naught conjugate plus h conjugate minus z naught into z naught conjugate divided by h into z naught plus h modulus plus z naught modulus. So this will be equals to z naught cancels out. You simply get z naught into h plus z naught bar into h plus h bar divided by h into z naught plus h modulus plus z naught modulus. Okay. Now, so now, I think this is z naught into h bar. I think so. Sorry about it. Okay. Now I hope it is clear. Z naught into z naught bar cancel, so that is not a problem. Now, as h tends to 0, okay, so okay, if you remember what is z plus z bar, it gives you 2 times real part of z. Okay, so the first bracket you can see it will be 2 times real part of z naught bar into h plus h mod whole square divided by h, and you have this z naught plus h modulus plus z naught modulus. Okay, now if you consider 2 axes, let us say I am considering the x-axis and the y-axis. If I had considered my h to be lying on the x-axis, okay, and h tends to 0 along the real axis. If I take h tends to 0 along the real axis, then what I will get? See, so h is in that particular case a real entity, so that is not a worry. What is z naught bar? So let's say z naught is x naught. Let's say z naught is x naught plus iota y naught into h. And if I'm talking of the real part, so it will be simply x naught into h. So what you will get? You will simply get this h naught mod whole square will go to 0. Here it will become 2 z naught modulus. So if you think what it will be simply 2 limit h tends to 0. This will be 2 times real part, sorry, 2 times x naught into h divided by h into 2 times modulus of z naught. So 2 cancels out. So it is nothing but it is equals to what? What is x naught after all? X naught is a real part of this thing only. Or you can write this is nothing but simply x naught not equal to 0. Okay, so uh, not equal to 0, and because we are considering z naught not to be equal to 0, so we'll have to write that x naught is not equal to 0 and y naught is not equal to 0. Okay, in other words, you can really see what it is. It is nothing but it is equivalent to writing real part of z. Okay, this modulus of z is also here now, so it is divided by x naught square plus y naught square. Okay, so it is real part of z divided by modulus of z naught. Okay, so this is real part of z naught divided by modulus of z naught. Okay, now if I take another path, let's say if I take this path, that is along the y-axis, then I will obtain limit h tends to 0. Okay, limit h tends to 0, and sorry. Oh, I'm so sorry. So what I'll get, limit h tends to 0. Uh, Here I know it is already 2 times real part of z naught bar and h plus h modulus square. I'm just writing this portion only. And now I'm approaching along the y-axis. That is the imaginary axis divided by h into modulus of uh, z naught plus h plus modulus of z naught. I'm just giving you a minute. Think about what will be the answer if I approach along the imaginary axis. Just think about it. Just a minute. I'm giving you a minute. Try to think about it. Okay. So if I approach along this direction, so h would be some iota. Let's say I would write h. Okay. So that it can be justified that I'm along the imaginary axis. And what is z naught bar? Z naught bar would be simply x naught minus iota y naught. So real part I will only get if this iota h multiplies with this. If iota h multiplies with this x naught, then I cannot obtain the real part. It will become imaginary. So the answer would be limit h tends to 0. This is imaginary z naught divided by modulus of z naught. I'll write this as 1 and I'll write this as 2. Now, since 1 and 2 are different, so if I approach uh, in two different directions, if I try to approach h tending to 0 in two different directions, I'm obtaining two different limits. So therefore, it implies that fz is non-differentiable is a non-differentiable function at z not equal to 0. So if z naught was equal to 0, then also it is non-differentiable. And if it's z naught is equal, if z naught was equal to 0, then it is also non-differentiable. We have seen that in last class. In this class, we have seen that z naught is not equal to 0, then also fz is non-differentiable. So one must understand that this is the basic difference, that when we were discussing the real function, the real modulus function, that is f from R to R, modulus of x, that particular function was non-differentiable only at a point and continuous on R, but its complex analog map, that is from f defined from C to C, modulus of z, is differentiable nowhere and continuous everywhere in C. Now let us take one example which is non-differentiable, sorry, which is differentiable only at a point. So since we have seen a function which is differentiable nowhere, now we'll see, okay, let us take another example which is differentiable nowhere, so that at least you'll get something. Just think about this function. What about real part of Z? What about a real part of Z? Is it differentiable everywhere, or it is differentiable nowhere, or it is differentiable only at a point? Let us see it first. So let us consider Z naught to be a point in C, and let us say H tends to 0, and let me write H as equal to H1 comma H2. Okay, let me write it as H1 plus H2, both converging towards 0. Okay, so both are quite small enough. Okay, and certainly this is not equal to 0, no? This is not equal to exact 0 comma 0, but both are converging to 0. So basically what I want to say is that H tends to 0 implies that H1 tends to 0 and H2 tends to 0. Or you can also think this way. You can take H1 to be completely 0 and let H2 tends to 0. And you can take H1 tending to 0 and you can take completely H2 equal to 0. That is, you can approach along two particular axes also. That is also one of the ways. So let us see how things would go. So let me, if real part of Z, if I have to check the real part of Z to be differentiable or non-differentiable, I need to evaluate this limit, f of Z naught plus H minus f of Z naught divided by H. I have to evaluate this limit. And this will be equals to what? It will be equals to real part of Z naught plus H minus real part of Z naught divided by H. Okay. Now, if I approach again, see, if I approach along the real axis, so for us part this, if I approach along the real axis, let us say that H is again H1 plus, instead of H2, I'll simply write iota into 0. Okay. So if I approach along the real axis, that is, if H is purely real, except 0, obviously, then what will happen? This will give me what? This will simply give me uh, what is x naught? Z naught would be simply x naught plus iota y naught. And this H is purely real now, so I'll write plus H1. So it will be x naught plus H1. So real part here would be x naught plus H1, which is nothing but, so I'll get here, just let me write, it will be x naught plus H1 minus x naught divided by H. So it is nothing but it is real part of H divided by H. And I know that I have taken H in a way that it is H1 only. So this particular value would come out as 1, because you see, I have taken H is equal to H1 plus, sorry, I have taken H is equal to H1 plus iota into 0. That is, I am along the x-axis. Okay, so I'm along x-axis and I'm tending H, I'm right, letting H tends to 0. So it is real part of H divided by real part of H, which is certainly, if you cancel out this, you'll get simply 1. Now, what if I approach, if I don't approach this way, what if I approach this way? That is along the imaginary axis. So along imaginary axis, if I want to write, H would be 0 plus some iota H2, and obviously it belongs to purely imaginary numbers. So I'm just trying to, okay, so this means I'm talking of purely imaginary entity, which is tending to 0. So now this will give me, again, so this is limit h tends to 0. This is real part of, I'll write once, this is x naught plus iota y naught plus, what would be h? H now would be simply iota h2 minus real part of z naught, which is x naught plus iota y naught divided by simply iota h2. Now what I will get? Limit h tends to 0. This is x naught. Here you'll get x naught, and here also you'll get x naught only divided by iota h2. and this is certainly 0. So clearly, if I am trying to find whether this is differentiable or non-differentiable, the limit f of z naught plus h minus f of z naught divided by h, this turns out to be real part of h divided by h, and it is 1 if I was talking about the imaginary part. See here what it is. It is simply real part of h is 0, because now when you are considering the second case where h was completely imaginary, so real part is 0. So I can justify with this expression, this is 0 if h is purely imaginary. And if h is purely real and it is tending to 0, then the limit is 1. Clearly two different directions, two different limits. So therefore, real part of z is also nowhere differentiable. Okay, so we'll see all these things later on also when we are going to do the Cauchy-Riemann conditions. But right now, at least I've done. So similarly, on similar lines, you can also prove that imaginary part of z is nowhere differentiable. On similar lines, we can prove that imaginary part of z is nowhere differentiable. In fact, you can also prove that argument of z and even z bar are also nowhere differentiable. I'm leaving this as homework. Try to do it on your own. The same approach that I've taken, you try to take two different paths, show that there are two different limits. So therefore, it is non-differentiable. Now, before we move on to Cauchy-Riemann conditions, let us write a few more things. Let's write the algebra and everything. Okay, before doing that, let us try to discuss one function which is differentiable at a single point. So let us find a function. Let us write a function fz which is differentiable only at a point. So, for example, mod z whole square. You know what is mod z whole square? It is x square plus y square, and you know that fxy is equals to x square plus y square, whether you write this way or you write it simply mod z whole square. This is one and the same thing. If you visualize, what is x square? X square is a continuous function. What is y square? Y square is a continuous function. So sum of two continuous function is also a continuous function. So clearly this is a continuous function on C. It is a continuous function on C. But is it differentiable everywhere on C? But is it, sorry, I'm asking the question, but is it differentiable on C? But is it differentiable on C? This is the question. So let us first try to find at 0. How does it behave at 0? So let us first find whether this is differentiable at 0 or not. So it will be f of h minus f of 0 divided by h. And it will give you what? It will give you mod h whole square divided by h, and this certainly equals to h into h bar divided by h. So it will be h bar, and if h tends to 0, so it implies your h1 tends to 0 and your h2 also tends to 0. If I'm saying h is nothing but an ordered pair of h1 and h2, then both tends to 0. So similarly, if I'm talking of h bar is what? It is equals to h1 comma minus h2. So this will also tend to 0 only, because h1 tends to 0 and h2 tends to 0 implies h bar also tends to 0. So this tends to 0. It implies this, and this tends to 0 along any path, because you see both of them are, if h is tending to 0, it implies h tends to 0 and h2 tends to 0. So obviously h tends to 0 and minus h2 also tends to 0. So irrespective of path, this limit is 0. So it implies that modulus of z whole square is differentiable at 0. Now what about other numbers? Or what about other numbers which are not equal to 0? So let us consider z not be such that it is not equal to 0. And let us now try to evaluate this limit. So this will be limit h tends to 0, f of z naught plus h minus f of z naught divided by h. So this will be simply z naught plus h mod whole square minus z naught mod whole square divided by h. And this will be z naught plus h into z naught bar plus h bar minus z into z naught bar divided by h. So what you'll get? You'll simply get one thing, which is limit h tends to 0, and you'll obtain z naught into h bar plus h into z naught bar, okay, plus h mod whole square. Okay, this is something that you will get divided by h. And now after all, you will get this as equals to z naught plus z naught bar. Okay, okay, sorry, not z naught bar. You'll get z naught bar, this is first, plus z naught divided by sorry, h bar divided by h multiplied plus simply h bar. Okay, now you take two sides. You take one side which is along the x-axis. So let me take one side which is along the x-axis. So let me write h is equal to h1 plus iota times 0. Okay, so basically now I'm talking of real axis. So if I move along the real axis, what I will get? So this particular portion, let me write in two different limits. Let me write two different paths, and let us see if h approaches 0 along two different paths, what would be the answer. So it will give me simply z naught bar is fine. This will turn 0, that is fine. Now this is z naught divided by, what is this? This would be h1 divided by h1. So you'll simply get answer as z naught plus z naught bar, which is nothing but 2 times real part of z naught. Okay. Now what you will get here? Here is if I approach along the imaginary axis. So let me write h equal to 0 plus iota h2, where h2 tends to 0. Okay, now what you'll get? You'll simply get z naught bar plus z naught. What is iota h2 conjugate? It will be minus iota h2 divided by iota h2 plus iota h2. This turns 0, don't worry about it. Now what about this? This will become z naught negative plus z naught bar. So this is minus, I think if you remember, z naught minus z naught bar is 2 times imaginary part of z naught. So it will be minus 2 times imaginary part of z naught. So clearly, two different paths lead to two different limits. So therefore, fz is equal to modulus of z whole square is differentiable only at a single point. Only differentiable at only single point, that is z equal to 0. So this particular example serves, this particular illustration serves as an example of a function which is differentiable only at a point and otherwise it is non-differentiable. One thing you have to keep in mind that the formulas for the derivatives of the complex functions are same as those of the real counterparts. So that you have to remember. That is, whatever formulas you studied in your previous what you can say in your previous times in real analysis will remain the same. For example, if you are told to differentiate sine z, it will become cos z. However, the the logic is different. There, the logic is slope and all those things, but here, any such uh, interpretation is not valid. Okay, so sine z is simply e raised to power z minus e raised to power minus z upon 2 iota. Okay, so if you really think what is e raised to, sorry, if you really want to write what is sine z is simply e raised to power iota z minus e raised to power minus iota z divided by 2 iota. If you differentiate it, what you'll get? You get iota e raised to power iota z minus iota. So this will become plus e raised to power minus iota z upon 2 iota. So you cancel this iota out. What it is? It is cos z. Okay, so I'm just giving you examples that, okay, these are uh, the formulas remain the same. So you have to remember the formulas. Let's say, what is x? The derivative of x raised to power n is what? N times x raised to power n minus 1. So similarly, if I'm saying what would be the derivative of z raised to power n? So it would be n times z raised to power n minus 1. Now let us discuss some algebra. So if f and g are differentiable at z naught, then their sum, okay, the difference, their product, quotient, provided g is non-zero, so provided g z naught is non-zero, are also differentiable at z naught. So if f and g are differentiable at z naught, then alpha f plus minus beta g, f by g such that g z naught is non-zero are also differentiable at z naught. Okay, this is important point. This comes from the, I think this particular thing you can find on in the books also. So I'm not going to derive it. Now let us write one more important thing. Let f be defined from d to d1 to c, and g be defined from d2 to c, and it is such that f of d1, that is the range of d1, is contained in d2. Range of d1, range of f is contained in d2. Now if f is differentiable at z naught and g is differentiable at, let us say, w naught, where w naught is what? It is nothing but fz naught, then the composition, then the composition g of f, okay, is also differentiable at z naught. Okay, so g of f is also a differentiable at z naught. I hope you'll find all these proofs in the books. I'm not going to dedicate much time here. Now let us define two important points, and then we'll conclude the lecture. In the next lecture, we are going to continue with the Cauchy-Riemann conditions that are very important. So you have to pay attention. From next lecture onwards, you have to pay special attention. Okay. So now let us first discuss what are analytic functions. Okay, differentiability is fine. Now let us discuss analytic function. So what are analytic function? A function is said to be analytic is said to be, sorry, is said to be, writing is not coming, is said to be analytic. A function is said to be analytic or Another word for analyticity is holomorphy. So, it's said to be holomorphic. A function is said to be analytic or holomorphic at a point A belongs to C if it is differentiable. If it is differentiable. If it is differentiable. Now, when we were talking differentiability, it was a local concept. That is, we were talking about differentiability at a point. Now, when we say that a function is analytic, then it must be differentiable at that point and at some neighborhood of A also. So if it is differentiable at every point, in some neighborhood of A. So this is something that you should remember. Okay. So when we are talking of differentiability, then it is fine. It can be differentiable at a point. But when we are talking of analytic function, then it must be differentiable at that point, and also it must be differentiable in some neighborhood. And when I'm talking in some neighborhood, it implies at each and every point contained in that neighborhood. So only then the function is said to be analytic. Now, instead, if I'm not writing point, and if I want to know the set, analyticity on set, then how would I define? So I'll say that f is analytic on an arbitrary set, let's say S, if it is differentiable. If it is differentiable at every point, at every point of some open set. Some open set containing S. Okay. So now if we are talking of arbitrary set S, if I'm saying that function is analytic on an arbitrary set S, then it must be differentiable at every point of some open set containing S. So instead, when we are talking of a point A, then it must not be differentiable at only point A, it must be differentiable in some neighborhood of A. That is at every point in some neighborhood of A. And what is neighborhood? Neighborhood is after all an open disk, okay, an open set. So same way, if we have to extend this definition on set S, then F is said to be analytic on an arbitrary set S if it is differentiable at every point of some open set containing S. So on the similar lines, we've written the definition for analyticity on the set S. The points where function ceases to be analytic are called as singular points, and those singular points we are going to discuss later on. It's not that simple, as I've mentioned right now, but still, on loosely speaking, I can say that the point at which function ceases to be analytic is called a singular point or a singularity. And we are going to see a lot about singularity in later discussions. Okay. Now, if I'm talking of a closed region, so for example, if I say that f is analytic, if I'm saying that f is analytic on closed region, let's say mod z less than equal to r, then it does not imply that uh, it is analytic only here. It implies f must be analytic in some domain containing this. Okay, in some domain containing this closed region. Okay. So one has to remember all these things, and the way we have already done a few things, I'll do. The first thing would be uh, the definition for the sorry, algebra for the analytic functions. So linear combinations of linear combinations and finite products of finite products of analytic functions in an open set D are also analytic, sorry. Okay, are also analytic. Okay. Uh, Functions which are analytic on the finite complex plane are also called as the entire functions. So another thing that you should write is entire function. So what is an entire function? A function which is analytic on the finite complex plane are entire functions. Okay, this is entire functions. Similarly, we can write that if f and g are entire functions, then alpha f plus minus beta g, f into g, and in fact f of g, if it is defined, are also entire. So the first thing that you should keep in mind that in differentiability, we were only talking of differentiability at a point. Now, when we are considering analyticity, we would be considering the differentiability in the neighborhood of that point also. So if I'm saying that function is analytic at a point A, then it must be differentiable at point A also, and also in some neighborhood containing A. Okay. So in every point on every point of that particular neighborhood, I would want my function to be differentiable if I'm claiming it to be analytic. If a function is analytic on the finite complex plane, on the entire complex plane, we are not talking of right now the extended complex plane. We'll only talk when I'll introduce you the notion of the stereographic projection. But right now, just think that if you include an infinity, then it becomes an infinite complex plane. And if I'm talking about finite complex plane, then the function which is analytic on the finite complex plane are called as the entire function. And they also follow the same algebra. And just again, pay attention to this point that if it is analytic, it must be analytic. It must be differentiable not only at that particular point, but also must be analytic, also must be differentiable in some neighborhood containing that point. So for example, I'll let you take an example. Let's say fz is equal to, I took an example of mod z now. So I'll take z minus a whole square. Now this is differentiable at a. I told you this serves as an example which is differentiable only at a point and it is differentiable nowhere. So basically, if A is some point in the complex plane, let's say this. So it is differentiable at a point A. So it's differentiable at point A. But is it differentiable anywhere? It is not differentiable anywhere. So it will not be differentiable in any neighborhood of A. So if I take this neighborhood also, it is not differentiable in any neighborhood because fz is equal to z minus a whole square is differentiable only at a point A and otherwise not differentiable. So if I don't take z equals to A, so then it is non-differentiable. So fz is non-differentiable for all those points except z equal to a. Okay. So clearly, in the neighborhood of z equal to a, you will find points other than a also. So if it is non-differentiable, so therefore it implies that fz is equal to modulus of z minus a whole square is nowhere analytic. Nowhere analytic in C. You have to remember this. See, again, I'm making the point very clear that if I'm saying that function is analytic at a point A, then it must be differentiable at point A and it must be differentiable in some neighborhood containing that point A. Okay. Now, when I took an example of fz is equal to z minus a whole square, I know that this is only differentiable at point A. Except point A, it is nowhere differentiable. Okay. So if I rule out A, then it is nowhere differentiable. Now, if you want to construct a neighborhood of A, you ought to have points other than A. Now, if it is not differentiable at all those points, in fact, however small neighborhood you try to make around A, it is never going to be differentiable. So in any neighborhood of A, it is non-differentiable. So, and otherwise it is non-differentiable. So it can, so analyticity cannot be written for points other than A. So it is non-analytic for all the points except A. Now, what about A? Can you make a neighborhood around A where function is analytic? Answer is no. So fz is equal to z minus a whole square is nowhere analytic in C. Okay. So by this, I'm concluding today's lecture. In the next lecture, we are really going to start with a very important concept called as the Cauchy-Riemann conditions. And I hope you're going to pay a lot of attention in those classes. Till then, take care. Bye-bye.